This session is Multipath TCP, and I present your speakers. Thank you very much for attending.
All right, so before we get started, who are we? I'm Catherine or Kate Pierce. I'm a security consultant at NeoHapsis who's read way too many RFCs for this. My accent is from New Zealand, for those of you that are guessing, and there are normally 4 things I get when I say that. Something about sheep, something about Lord of the Rings or Hobbits, Flight of the Conchords, and your cousin who went there last year. I don't know them, okay? And with me I've got Patrick Thomas, a senior security consultant at NeoHapsis, and he has an application security focus. Okay, so why are we here? We're here because Multipath TCP changes fundamental assumptions about how TCP works and how you can use it to break things today and how we can prepare and adapt for it tomorrow. Well, kind of.
All right, with TCP here, can we get this mic? You good there? All right. If we're not talking about layer 4, things are totally the same. If we are talking about layer 4, that's where things get interesting. So I'm going to start you out with 2 simple examples for how MPTCP changes the things that we're used to seeing with TCP. All right, curl. This is very simple. We should all have a good mental model of what this does under the covers when we do something like this. So let's see what actually happens. Put it through Wireshark, take that first GET request, and follow a TCP stream. We should be able to predict what this does. The problem is that it does something different than we expect. We see the GET just fine, the whole request is there, but nothing in the TCP stream for the response. That TCP stream is closed and gone, and there's no data there. But we saw it in the console. We saw the data come back. Where did it go? Where did it come from? Example 2. Let's simplify it even more. Netcat does nothing except open a connection. Should be one connection. Again, simple mental model of what's going on here, except that it's not simple. That one simple netcat command opens all of these connections. You'll notice there's connections to different IP addresses, to IPv6 addresses. All right, what's going on here? Why are we seeing this? This makes no sense. So we're going to talk about why do we see that. Let's talk about MPTCP. But first, why do we need to change TCP? So what has driven this initiative? Why are we expanding it? Well, there are some limitations which are becoming more and more common, more and more prevalent in some of the things we see. TCP native doesn't support use cases for high availability because it's one-to-one. Doesn't do link aggregation, again, one-to-one. You can't multi-home, you've got to drop and start a whole new connection. If you want to do mesh networking, well, I'm not going to get started on that. Multipath TCP. It's an extension to TCP, so it's bolted on, strapped onto TCP that adds functionality to deal with the above. Because it's an extension, it works on most existing infrastructure, because it is TCP. However, nothing much else understands it, even the devices that pass the traffic, including security tools. So the basic use cases for this, which relate to what I said earlier. Seamless roaming, if you're going from network to network to network and changing IP at each step, that's one of the things Multipath TCP helps with. Or if you're using high availability or highly connected data centers with connections all over the place, it also helps with that. To be clear, because there's been a lot of media spin about this talk, Multipath TCP is more about a culture shock than an explicit security vulnerability. That doesn't mean it's not important, it just means it's not a vulnerability. It's more fundamental than that. The two of us, we like this. We like the tech and we think it's really, really cool. We want it to succeed and no one is ready to help it succeed right now. Security is panicking whenever they see this. Everyone we talk to does not know how to respond. So we want it to succeed. We want you to get ready. So I guess we should start with some background. What got me thinking about this? Sometime last year, around September, I came across an article on Hacker News.
Apple seems to also believe in multipath TCP. I had no idea what that was, so I clicked on it. It took me to a blog post by Oliver Bonaventure, one of the professors who had his team working on this stuff over in Belgium, because it's primarily European people developing this. Anyway, massive credit to them. But that contained a Wireshark capture, which was interesting, and it piques my interest. And around the same time, I started seeing media coverage coming up. Some big name things. And the register throwing in their normal stirring the pot. And then what happened next was strange. We had something deployed on hundreds of millions of devices, and people just completely stopped talking about it. That seemed weird. So I started looking at it. The thing is, while no one was talking about it, for a fundamental change to a core networking protocol, this is coming along really, really fast. It's been in development 2 or 3 years. It's about 15 versions into the RFC. It's big, a lot of implementations, but no one's talking about it. And more importantly, no one was talking about security. The people who developed it looked at the thing itself. And so, in terms of what it means, it's about as good as TCP. But because it's so fundamentally different in what it does and how it works, it means a lot of other implications come along. And this can mean huge things to network security that no one was talking about. And that's what this session is about. What does multipath TCP mean for security today? And what could either this or some other similar multipath networking technology mean a decade from now if it's rolled out widely? And being Black Hat, a couple of attacks, tools, because I've got to make it concrete. Okay, so that's the fluff. What's the tech? TCP implements connections IP port to IP port. That's in the specification, Connection-Oriented Networking 101. Now that's not between the endpoints. That's between IP and port, IP and port. It's usually been a distinction without a difference, but it's no longer the case. What are the characteristics of multipath TCP? What are the things that they were trying to design into it? Backwards compatibility. So SCTP did do some of this functionality, but it didn't get widely adopted because it required a lot of rewriting of software, hardware, networking things. And you know what? That's understandable. Multipath TCP is backwards compatible. Performance at least equal to now. If it's worse than now, why would you use it? Security greater than or equal to now. Who knows what that means? And it rides on top of TCP, as I said earlier. A connection is defined by a connection ID. We'll get into the details of that a bit later. And a multipath stream is comprised of multiple TCP streams that are mapped together. Each of those has that option strapped on with the details needed to tie it together. So, if you're doing one connection, even with multipath TCP, it looks the same. One network, one connection. Okay. But if there's another network, 2 connections, same data flow. Or rather, n different connections, possibly across the same path, but still one logical data flow. Data flows through any or all. You can send any part down any part. We'll get to that later. The thing is, when I said you can send it, the packet sender decides which data goes down which path. That's going to be important later. Any subset of those connections can drop, and it will keep going. If you don't kill them all, they're going to regrow. You can re-add them at any time. One of the interesting nuances that we haven't looked into a whole lot is that If an acknowledgement doesn't come through, you can receive it across another data flow. Send data that way, hear OK from over there. At the MPTCP level. So it's a TCP option. It sits between the standard TCP header and the packet data. It's got its standard header, 0x1e, so option 30. Length, normal TCP option stuff there. Subtype, I'll get to that in a moment. Version and flags. It's just some stuff shoved into a TCP header. Not surprising so far. When you look at it, Wireshark supports this in the later versions. You can see it. TCP option 30. So I mentioned those subtypes. A multipath TCP subtype is a message that achieves a specific purpose within a multipath connection. There are 8 of them currently defined. Multipath capable. That is sent an initial handshake just to indicate, I support this. That's all. Join. If a connection comes in, it can authenticate to an already existing connection. DSS, data sequence signal, that maps each individual subflow's data against the overall connection data. Add address. I can tell, I as a client or as a server can tell the other party, I have other addresses. Feel free to use them. Or stop using one I've already advertised. And there's a few others that we'll leave for now. We're glossing over a lot of detail just to get to the interesting stuff. So in the Linux implementation, which is the easiest to get and to use today, there's 2 primary path managers. Full mesh, every interface to every interface across every possible path. So this is a factorial arrangement. And end of ports. One interface, multiple ports, down to the destination on the other end. It's a bit abstract, but that's in the TCP stack. Because this runs in the TCP stack, because this runs at the socket layer, your applications get this for free. They have no idea this is going on. That's why it's great for interoperability and for rollout. But it means you can use tools, including security attack tools, that have no knowledge of this protocol. So what I said about end of ports, it's 1, 2, 3. Multiple ports to 1 at the other end. These specifics of these things don't actually matter for now. These are just 2 extremes. In future, who knows how implementations are going to decide to use these capabilities. These are testing ones, but they're interesting to play with. So full mesh, as I mentioned earlier, every interface to every interface. So all of it's interface 1, 2, 3, 4. And you've got a spider web. So some slightly deeper technical details. The way this is all set up is it's a TCP handshake, a standard TCP handshake with some additional stuff flowing in the options. The data sequence numbering is not just a random number sent through, it's a truncation of a SHA-1 of a key sent through. Don't worry about that for now, but I can talk with anyone later if they want to. So those keys that are sent through in that first handshake, they're used to authenticate at later points. Challenge response, so you can't replay it, and HMAC, so you have to have knowledge of that secret. Except it does send plain text keys in the initial setup, and also in a quick teardown, the fast close. We might talk about that later, but we'll leave that for now. So I said earlier, the packet sender decides where the data goes. That's going to keep coming back to that, because that leads to some fun things. So the first thing we're releasing is just a very quick cheat sheet on this stuff. There's a lot of detail. I've spent many nights banging my head against RFCs, against the wall, against the bottle, trying to figure this stuff out. So some of the stuff I've learned, I'm giving to you, because don't go through it, please. It was painful. So I've talked about it and roughly how it's implemented, who's using it. Not much. Today, it's not used a whole lot, with a couple of interesting exceptions. As I said earlier, iOS 7 uses this for Siri. So if your Wi-Fi drops out in the middle of a Siri communication, you shouldn't notice because it should switch seamlessly to Wi-Fi. The rest of the handset has no access, just Siri. And there's some other experimental stuff for high bandwidth, high flow supercomputing, but really, it's not there at large. But considering it's not out there at large, there's a lot of implementations. Yeah, Linux, BSD, Android, and vendors are putting varying degrees of support in, whether it's making it so their equipment doesn't kill it by default, or talking about putting it in, or actually putting it in. There's several big name vendors that have talked about this. However, not Windows, not Microsoft. Who knows? I don't. If it comes along, it might. The thing is, if it doesn't come along to Windows, that's going to really hinder adoption. But if there's enough pressure, maybe it will. It's also quite easy to get it working when you're playing with it as a security person. The Linux implementation is the one I will generally recommend. The reference implementation has Debian packages, and they work in Kali if you want to spend an evening working out routing, but it works with almost all of the tools. So there's also a really, really cool implementation of this stuff hooked into Scapy, which enables you to do packet crafting. He did an awesome job. We fixed a few bugs as I was making it interoperate, but props to him. He did some really, really cool stuff, and frankly, I don't think he's getting enough attention. He's got 3 stars on GitHub. I think we can fix that. Okay, enough about the thing. What does it mean? What are the security effects? Cross-path traffic fragmentation, which is the whole point. Half your traffic that way, half that way. Okay, that is the whole point. Moving target, adding and removing addresses as you go through a connection. Whatever you start with is not necessarily what you end with. Connection resilience. Until I kill them all, I can't guarantee that the whole connection is dead. So if I'm sitting there with an IPS trying to reset connections, I'm going to have a bad time. Oh yeah, and there's also checksum, so if I try and manipulate data along one path, it's going to drop that path. And they're not very easy to fake. And that thing about adding and removing connections. I give you an address, the server connects to the client. Talk about that in a minute. So, because of those things, cross-path, moving target, resilience, reverse connections. If your approach to security requires any of those assumptions, it's going to start breaking in this world. If you expect to be able to see all of the application data on a single TCP stream, if you want to differentiate your clients from your servers based purely on that SYN packet, if you want to start, changing the data flowing through, or you presume that that IP address means something, it's not going to work so well. And something's going to break. Okay. How practical are these attacks? What can I do with them today? A lot. But only if both endpoints speak multipath TCP, and by and large, it's not rolled in by default. So you have to have root on both ends. You might have that on a pen test if you completely own a box, but in most cases, you're hopefully not giving all of your users root access. So it's not a great risk today. However, in a multipath world, whether it's MPTCP or something else, these attacks become a little less practical because you're going to see it and know what's going on, But we still have to change things. We can't do things the way we've done them. Network security has to adapt. You can partially mitigate them if you're aware of it. You can correlate the things you do see. So if you have multiple streams and you see them, great, you can strap them together, you know what's going on. But it still changes how networking works and how network flows work. And if some nefarious security researcher, should we call them, goes in with well-meaning intent, we can break all sorts of things. The packet sender decides what data goes down which path. Now, normal or benign clients don't choose pathological, really messed up fragmentation schemes. They don't send a byte that way, that way, that way. They do it efficiently. But that doesn't mean we have to.
So benign clients, they're going to do something sensible, something reasonable, but there's nothing stopping us from doing that. So let's get practical with this. We've been talking about, hey, you can split this traffic across all sorts of different paths. What does that look like? What is a practical effect for attackers right now? So this tool is a tool for IDS evasion. Send whatever payload you want through the tool, and it gets fragmented down as many paths as you want, split evenly. Actually, I can't see it started. Aiming off to the side. There we go. All right, we're using Snort here just as an example. This works just as well on any of them. There's a really cool distro called Security Onion. If you want to play with IDSs, definitely check it out. So the UI would be a little bit slow for us. We're just going to actually tail the alert log here. So anytime we get an alert, it'll pop up right there. All right. So once that's running, go ahead and get our tool up here. So the fragmenter and the -N1 says, let's just send this over one path. This is the degenerate case of MPTCP. Send a payload to a server, open up one stream, send it, and the IDS immediately says, hey, something wrong with this. A simple detection, kind of a dummy payload. But if we come back and say, all right, MPTCP, let's open up 5 streams. Let's split the payload into 5 just evenly across these streams. Regular old TCP going down each stream, just 1/5 of the data each way. Open up 5 streams. Send some data. And a distinct absence of an alert in the IDS. So, okay, why didn't Snort see it? It's the exact same tool. All we're doing is splitting it over some different traffic. So here's Wireshark, that exact same run. If we go grab any of these streams at random, I think go grab the first one here. Do the stream follow that we showed you at the beginning. And here's why. Here's what an IDS sees because it doesn't know how to correlate across different MPTCP streams. It has no idea that, that they're related right now. Just the beginning of a GET. That's not even a completely well-formed GET because the rest of that request went down the other channels. And we could have picked out any other one. We would have seen an individual snippet. So this is TCP, but not as we know it, essentially. So this is one of the tools that we're releasing. It's actually up on GitHub right now. We'll have a link out at the very end of the talk. All right, this.
Okay. So obviously this change in flow has some difference for perimeter security. But what does that mean? Well, it means your firewalls are going to start seeing some interesting things. How would you like an outbound incoming connection? Outbound, but incoming. That makes sense in the multipath TCP world. What do I mean? Okay, so let's set that up. Set up our multipath connection. SYN, SYNAC, ACK. Okay, it's a TCP connection. Well, let's tell the server that I have another address. In the specification, that server now has the option to set up a connection back to that address. Is that incoming or outgoing? You're talking about your firewall policy. What does that mean? I've been staring at this for 9 months. I still don't know. Yep. I'm with the kitty. I don't know what's going on. I'm confused.
All right, network management in your infrastructure, in your data center. The point we're getting across here is that if your tool doesn't understand MPTCP, if it doesn't read those options, if it can't understand that multiple TCP physical flows are related to a larger logical flow, then they simply look unrelated, and you're going to get little tiny snippets of garbage traffic on each of those TCPs that you look at. This is Firefox requesting a web page. All of those little yellow things ringing around the side are address labels for different connections that got open. Now, of course, we cranked this up to make it full mesh and as obnoxious as possible. But the point is, this is a perfectly reasonable connection. It is a perfectly reasonable activity on your network. And yet, if you pull it in Wireshark and do the show all endpoints, you get something nonsensical like this. On the network, if you don't understand it, but you at least cluster by IPs, these are IPs that are shared by devices, you start to see a little bit more sense. What we really need to do is get to the point where something actually understands that, hey, there's all of these different TCP connections that are participating in one logical MPTCP connection. All right, defenses, awareness.
All right. So if this is a threat to you today, what do you do? Well, the first thing is, know it exists. You're here, that's a good start. Make sure your technology knows it exists. Check support in your devices, and also look for it being used across your network. Understand if your architecture can cope with a multipath world, or if you can successfully control it and terminate it in the same way that we do SSL. Uncontrolled SSL, you have no idea what's going across your network. Uncontrolled MPTCP, you have a partial idea, but it's still messy. And to help with that, one of the things we're releasing is a scanner. Something which will scan listening devices on your network within a range and see if they actually understand this. You give it a host, a port, or a set of ports, and it will scan them. Okay, seems pretty simple. I have a thing down there, MP_join verified. What do I mean by that? I'll get to that in a moment. The scanner accomplishes 3 things in general. Verifies if the device pretends to support it. If it says, yes, sure, I do that. It tests it if it actually understands what it's saying or if it's just agreeing with you. And implicitly, it verifies that your network path lets that communication get there and back. That MP join verification I was talking about, if we do a SYN saying we're capable, and if the server replies and says, sure, I take that, you might think that was genuine. Unfortunately, there are quite a few systems, particularly I think China's Great Firewall, that just echoes the options back at you. It sends them straight back. And if you're not careful, you'll think it's things support multipath that do not. So we then send a join request to add a stream to an invalid connection. If it accepts it, it doesn't understand multipath, and it's just a standard TCP connection. If it rejects it, it'll reset it. And we know that it actually understands multipath. It's not just agreeing with us. Okay, so checking for support is one thing. What can you do? Well, you can make it so that it doesn't flow across your network. In the short term, people are probably going to be doing this quite widely. I don't know if it's a long-term solution, but it does work. You can terminate that connection, as I said earlier, with a transparent proxy. Whether it's about MPTCP or not is irrelevant, because you're just shoving all the data through one point. But you can also use some firewall rules, strip options 30 IP tables, or TCP options 30/30 clear on a Cisco device, or on some of the newer ones, you can actually do it with slightly different options. But you can just tell the firewall, if you see this, kill it. But it also affects your active network security, your actual IPS, as well as your IDS. To track and modify multipath TCP, some things you have to do that are far more complex than a TCP connection are: capture the handshake, where it first sends across some authentication data. That's used throughout the rest of the connection to verify things. If you don't have that, it's variously difficult to impossible to mess with this traffic. If you don't have it, or even if you do, you still have to perform non-trivial state calculations to determine which TCP connections belong to which overall connection, and are the checksums correct on your modified traffic. Sounds much simpler than it is. Okay, so that's what we can do today. What about in a hypothetical future where everything is speaking in this kind of tech? What do we do then? Well, before we get there, the things that scare network operators about multipath TCP are taking control away from them towards the endpoint. Now, if you're trying to protect yourself from your network operator, you can use that to your benefit. Because it shifts that power away from an ISP or infrastructure, or you as a network owner, towards that endpoint. I don't trust my ISP, and I trust my cellular company. They probably don't like each other. And it raises that bar for collaboration so much higher, I'm a little bit safer. Because they don't trust each other. Use their business models against them. Okay, how do we gain these advantages of mobility and of link aggregation securely when everything's supporting this? Well, some of it we can adapt, we can write it into tools. And some things you can't. Because things like physics get in the way, and that's somewhat difficult to circumvent. Say you've got an IDS on one path. It's not going to see traffic going across the other path, and it's going to see part of the traffic going across its path. If I'm sending ABCD, maybe I'll only see BD. What do you do as an IDS? There are many approaches to do that, but there are a lot of questions. Do you do some sort of probabilistic thing, some sort of similarity thing? I don't know. And that's the sort of thing we need to look into as an industry and as a discipline. Because it doesn't make sense when you see this traffic. So there are things that change our existing security models will not deal with, no matter what we write into our tools. If you're trying to monitor individual paths, even if they're collaborating about the flows, if you're not collaborating to reassemble that data, it's still not going to work. However, if you do things like split trust cryptography, or multipath agility, so split trust cryptography is sending part of your ciphertext or part of your IV down different paths. If you miss one, you might not be able to make sense of any. Multipath agility, if you're address hopping every few packets, sure, you can track that, but that's an additional layer of state. And if you're doing that through something that effectively anonymizes it, a tumbler of addresses, I don't know how you would deal with that. And there is some research into the privacy aspects already underway. I've got a few in the references, a whole lot more in the white paper. So, there are some other ideas we've got for research that we haven't quite got to yet. Stream hopping. Sending out a whole lot of streams. At any one point, only some subset of those are valid. So if you're sitting there watching that traffic, and you have no way to know which ones are actually being listened to, which ones are valid, it's an additional layer of obscurity. Oh yeah, and making proxy tools. You run this at both ends, and they do this network craziness between them. Didn't get as far with it as I like. It's coming along. Dealing with this state in addition to TCP is not fun. Mixing it with Tor. Now, I'm not about to do this personally because if you mess with Tor wrong, you get people killed, and I don't want that on my conscience. But if the right people look at this, and they look at the implications, and they think it's worth doing, maybe it could be big. Distributed networks on some sort of multipath thing. Too much to go into. Come back and look later, or ask us later. So another thing is, I said earlier that when you close a connection, those encryption keys are communicated. The reason that that is currently claimed to be safe is that the closing system has shut down its state. So it is no longer listening, it has just closed it. Thing is, if you're along that path and you intercept that, you can leave the other end open and then jump onto that connection. At least that's what my read of the specification takes. I'm a little more to look into that, but anytime you're sending plain text keys across the network, it can get risky. But at the same time, security no worse than TCP was their goal. It's not a very high bar. Conclusions. What does this mean? Well, I love this tech. This tech is awesome, and it's probably coming, whether it's this solution or some other. There's been a few abortive attempts over the last decade, SCTP notably, a couple of others, some of them quite big, but this is one that looks like it actually might succeed. Once you start getting implementations and vendors and RFCs, more chance of success. But it breaks the way we do things. It confounds business models, confounds security models that rely on inspection. So we may have to choose, like, do we go for the usability or do we go for the network operators? I don't know. But either way, we need to be ready, and at least in some basic sense. We need to prepare. And this is just to start the conversation. Okay.
All right, I want you guys to get your hands dirty. I'm going to put a PCAP out there that has a challenge in it. It's got some data. It's a couple of machines communicating using MPTCP, and there's some data flowing across that. And simple, tell us what the data is. Grab it all, reassemble it using whatever tools you want, and tweet it out at us. This link takes you to a full description of that, and my boss doesn't know it yet, but we're going to expense a $100 Amazon gift card for you guys. So as soon as you got it, hit us up with that, especially questions. This is intended to provoke discussion, not just enrich someone. So hit us on Twitter or wherever we're around afterwards. This is interesting stuff. We want to get it in people's hands, get people playing with it, get people talking about it and understanding what it does.
And just to look at the traffic and see how it works, what it does your tool handle it? This is a PCAP. This is one of our tools in operation that you can use and see, what does this mean? And then try and reassemble it. Questions? And our contact details and the repo where the code is, and it was released an hour back.
All of this is out now.
It's all out now.
Yeah, hi. Let's pretend I'm an enterprise network firewall administrator and I'm scared to death. Could I tell my firewall to sort of rewrite packets so that if my Siri phone is trying to talk back to Apple, oh, bummer, the phone thinks that Apple doesn't actually support this today. So I'm basically turning it off. It buys me a couple of years until it's required functionality. Yeah, so.
You can do that. The thing I'd caution you is if it's able to establish a connection, if you get on the first connection, yes, you can do that. But if it's already managed to set up that multipath connection and you do that, it's going to drop and go for the paths which do support multipath. So if you've got 10 open and you kill 3 of them, the other 7 are going to keep going. So you have to get that first one. On a mobile device, do you have access to the routing tables? Of an iOS device? Maybe the APN?
Yeah,
Bit of a Wi-Fi network?
good point. Quick other question. I was a little surprised about you were talking about sort of the checksums, and I mean, are they trying to go above and beyond, like the TCP, the purpose of the checksums is more about garble, that's not a crypto purpose, at least in my own mind, it's because you can reassemble TCP halfway between, right? So
the checksums are not intended to be cryptographic. They end up, because they are across a pseudo header, which includes information from the initial handshake.
okay.
If you haven't captured that,
Oh, okay. So it makes
can't do
it
it
harder
with
to be a helpful reassembler in that
Yeah.
case. Yeah, okay. All right, thank you.
And also to that, one thing that when you start looking at this, there actually isn't a single value in any of the MPTCP packets after that initial handshake that you can specifically identify one as a particular TCP connection as a member of an MPTCP connection unless you capture that initial part and unless you do some non-trivial math. It's not like integer equals integer. It's actually some HMACing, some hashing. So it's...
Thanks.
let's do that.
This is to some degree a question about the protocol itself, but I have, for example, 2 hosts on one network, and one of them is dual homed. Would I possibly see MPTCP paths trying to trace out through outside the network and then coming back in? So if I've got my internal network and one server has a external link as well, could a server with internal only connections use MPTCP to try and go outside into the open internet and come back?
I heard most of that. I heard most of what you said, so let me repeat it back to you and make sure that you've got 2 machines, you're saying a scenario, we've got 2 machines on the inside, and they're communicating, both MPTCP capable, and one of them has an address that is outside of that network.
You can do that.
Yeah, absolutely. One of the hosts can advertise, hey, I have this address, either, connect back to me. So that's one of the places where that can come in, and that's an option in the protocol. It's not at all mandatory. But also if it will just simply try to connect in, and that could potentially be allowed as well.
Yeah. That can be in as many different subnets as necessary.
So since only one endpoint really needs to roam generally, if you don't want to strip out MPTCP, why not just have an MPTCP terminator? Therefore, your IDS can see everything in standard TCP after the terminator, and you're good.
You could definitely do that. You'd have to make sure that you switch the encryption keys as it goes through. Otherwise, it could set up a different path.
Switch any encryption keys. You would that would be your terminator.
Oh, terminate it and
Nothing
TCP
past
thereafter?
it
Yeah.
is MPTCP.
It's equivalent to stripping it out. It just ends the TCP connection.
Yeah, but the other end can still roam.
Yep, you can do that.
So am I correct to understand that it's up to either the implementation or the application to decide what exactly it wants to get out of multipath TCP, whether it wants to get high availability or be able to use multiple paths for increased bandwidth? Was I correct in understanding
It
that?
is just the implementation, correct.
Okay.
Right now, they're talking about building an API, so you can give specific socket options about this stuff. That does not exist at present. So it's purely the OS and how it wants to handle things.
And you could also choose, it should be fairly small, not fairly simplistic, but possible just to build TCP connection and put it on top of yourself, or build sockets and do it without doing it in the network stack.
You could, and that's what our Scapy tool does. It just does that with raw packet crafting.
All right, thank you.
One further response to your question there is you're asking, it is absolutely an implementation detail as to what packets or what connections you use, how many you set up. And right now, the implementations that we talked about up here, the full mesh, the NDIF ports, those are kind of experimental just to show people how they can work. But as this matures, then we could see potentially more routing choices based on any number of things that might be important to a client. Cost, speed, latency, trustworthiness, any of those kind of things, all implementation details, you can build as much intelligence in as you want.
Hi there. Spoke briefly about privacy issues. Would it be possible to take something like an ADSL connection, my 4D connection, and split my sort of HTTP request across the two to completely annoy the NSA?
Yeah.
Yeah, and you get that, one of the use cases here is link aggregation. So if you've got, multiple unreliable connections, you can set up TCP connections on all of them and have all of those hot open and be able to send packets. And if you don't get a response in the amount of time that, if you don't get the ACK in the amount of time that you want, you can already start sending it over another one, and that higher level MPTCP state will make sure that the data is flowing through and logically reassemble it on the other side. So mesh networking, high availability, the aggregation, all of that stuff are huge use cases for this.
There's nothing to have stopped you doing these techniques in the past. You just would have had to write that yourself. Nothing's stopping you strapping TCP connections together, but this makes it so much easier and so much more transparent. Yeah.
Okay, thank you.
No more questions? All right.